We're going to now talk about two other things. When it was Resonessence, which is a small startup company in the same town where I live, suggested that I should come and talk at the Rocky Mountain Audio Show today, and the organizers did not want to drop these two topics. I suggested that perhaps the hyperstream modulator was interesting enough, but the organizers wanted to not lose track of these two. So I'm now going to do a shorter presentation focusing on two things, jitter and digital versus analog volume controls. And we're going to go through it a little bit more quickly than we did through the one that we just listened to. In order to understand, the question we're going to address is an analog or a digital volume control the best? And I don't like to leave you guys wondering. I'm going to tell you right now, an analog one is the best. But let's see if we can work our way to that conclusion. We need to know how a digital volume control works and what are its limitations. We need to know how an analog volume control works and what are its limitations. Here is how a digital volume control works. If we give the digital circuit a number, such as a number that I chose semi at random, that number there, and we ask the digital system to turn the volume down, as it were, how does it actually do it? Well, a digital system does it by just multiplying. If we ask it to turn the volume down to minus 10 dBs, minus 10 dBs is 0.3162, and therefore it takes that quantity and it moves it and creates that quantity there. Is this a problem? Well, the answer actually should have been that. And it's close. It's only wrong by 23 parts per million. But it ain't right. That number isn't right. That number is right. The difference is very small. If you ask the digital circuit to turn down the volume by minus 35 dBs, the digital circuit does that and gets 534. Is there a problem? The answer should have been that. And this is a little bit worse. It's 866 parts per million in error. And those numbers, 23 and 866 ppm, sound very small, but actually they're not. 866 ppm has degraded the 16-bit DAC by a factor of more than 50. And so we can quickly see that a naive, well, I won't call it naive, but a simplistic implementation of a digital volume control working on a fixed width data field of 16-bit numbers that the DAC receives creates a huge amount of noise because it cannot handle the fractional part of the number. And we're going to go to good old FFTs again. And in this FFT, we're going to use some of the design tools to show us what's called the equivalent number of bits is and what the signal-to-noise ratio is. So here's a signal coming along near full scale, and here is its Fourier transform. And this tool can analyze the Fourier transform and recreate what's called the equivalent number of bits. This is pretty good. We have a signal here at minus 1 dB, and the equivalent number of bits is 15.87, and it's a 16-bit DAC, so that's really very good. The same analysis on a signal 10 dBs down. That signal's dropped. Is it 10 dBs? Yeah, 10 dBs down from the original signal. And again, the analysis says we're not doing too badly. We've still got 14.35 equivalent number of bits left, and our signal-to-noise ratio is 88.51. But goodness me, look at this. Turn the volume down minus 35 dBs, and we've only got just over 10 equivalent bits and 63 dBs of signal-to-noise. That's equivalent to a pretty good cassette tape recorder of the 1970s. It's not very good by today's standards. So unless you like to listen to music exquisitely loud, very loud, you are not getting anything like the signal-to-noise ratio from the system if the system has a fairly simple form of digital volume control. There it is shown more clearly, and we see what's going on. The signal is coming down. The noise is staying just where it was and hence the problem. And this is why audiophiles generally avoid digital volume control, because they know that it's not suppressing quantization noise. It's only suppressing the signal. And so the signal-to-noise ratio becomes bad. Now, contrast that with an analog volume control. Now, these graphs are from a little simulator configuration that I have that shows me the trade-off, the best way to make an analog volume control. So it isn't the perfect system that you might imagine. Just watch what happens. At the high signal level, with the analog volume control turned down to -1 dB, it's very good. In fact, within the error, it's reading more bits than we've actually got, 16.01, 98.53 signal-to-noise ratio. But that's a numerical error in the analysis. Don't worry, we didn't get something for nothing. And then we turn it down to -10 dBs, and the analog volume control is still doing very well. It's still providing us 16 bits very nearly, 97 signal-to-noise, fabulous. We start to see the analog volume control lose it a little bit when we ask it to go to -35 dBs, because, well, it's still good. It's 14.94 bits, 91 dBs signal-to-noise. It isn't what you might think it is, because, of course, the analog volume control doesn't have zero noise associated with it. It does have some noise associated with it, so at some point, the noise floor just cannot keep going down. But generally, it does. The noise floor goes down with the signal in an analog volume control. That's why analog volume controls are better. But I said that digital volume control was simplistic, and it was simplistic because that was what you could do as a user of a 16-bit DAC. Those were the bits you had. You had the 16 bits coming from your music source going into the DAC. But for example, the Sabre DAC has an internal data path of 32 bits. And again, it's hard to understand what those bits do, but those bits do useful things. And again, it's just a repeat of that graph again. The Sabre DAC has an analog noise floor. This noise floor here is not limited by the digital data path. This is limited by the analog components of the part. And I guess while I'm here, I should say that one way that you can find this out from DACs that you buy, you can search for anomalies up here. You will find that most DACs have little spikes sticking out up here. And those little spikes are to do with fixed pattern noise that's propagating in the loop. But it doesn't matter. The point is there's a lot more digital bits available inside the chip than there are outside the chip. And indeed, if we represent those additional bits as being the 16 that come from the outside world and the 16 that the chip has inside, if the chip does the multiplication, it does fill the bits below the resolution of the signal applied. So as you put in the 16-bit quantities, the digital volume control moves the data into the lower LSBs, and it correctly represents the signal, exactly correctly. So when the digital volume control has access to additional bits in the DAC data path, there is no numerical loss of accuracy, assuming the DAC has all these bits in it, which most modern DACs these days do have those extra bits in them. And therefore, in that case, the actual output noise does fall with the signal. This is the digital volume control being told to decrease the signal amplitude, and look, the noise is going down with it. And the noise will keep going down until it hits the noise floor. Oh, that didn't work very well. Until it hits the noise floor. So it doesn't go on forever, but it goes on until it hits the DAC noise floor, which is a remarkable 135 dBs in the Sabre DAC. But is analog still better? Well, I'm afraid, or perhaps I'm not afraid, perhaps I'm proud. The truth is, yes, it is. An analog volume control designed with the same kind of care that we apply to our DACs will beat our DACs, because you can make an analog volume control with a very, very low noise. So you have to design it with care. You can't just buy a potentiometer off the shelf and connect it up. That isn't going to work. And you can't just put a regular amplifier on the output to drive the line to the power amplifier, that isn't going to work. But if you design an analog volume control with care, and it has an inherent noise floor in excess of below 135 dBs, that is still the best way to do it. So as I came to the conclusion there, an exquisitely well-designed analog volume control can still beat even the very best digital volume controls, as long as it has an inherent noise floor lower than that of the DAC itself. Right. And in a moment, I'm going to talk about jitter, but I'm just going to stop for a second to ask if there's any questions about analog volume controls. Yes?
So if you've got a 32-bit digital volume control, all right, the analog would still be better. I mean, would the difference in audio performance be perceptible to somebody?
No, it could be, my initial feeling is no, because we're now beginning to talk about levels of 130 dBs and in excess of 130 dBs. And even given my experience with listening to audiophiles and sigma delta modulators, I still have a hard time believing that you can hear below 130 dBs. So in the limit. But you know, if we're honestly asked, if ESS is asked, is it better to use an analog volume control? You say, look, if you have the resources and you spend money on it, the truth is it is at least as good, if not better, than the digital volume control. That's the honest answer. And lots of people do that. They do that. Although it's one of the most often requested features of our DACs. People want us to put in an analog volume control into the DAC. Yes?
Any hints what kind of analog volume control?
No, but I kind of alluded to it already. The engineer designing the analog volume control has to understand about thermal noise, and you have to make the thermal noise accumulate to no more than about 136 dBs. A quick analysis, you know, if you think, I'm just going to go crazy, you can probably get 136 dBs or lower out of an analog volume control. But like I say, you don't just choose a pot and turn a pot. No. You'd have to do it with precision switches, very low noise, very low on resistance switches. It's not a trivial thing. Yes, sir.
Analog volume controls as a ladder in a chip, like a PGA.
For instance,
yeah. I think they would come quite close.
They could. Yes, I think the answer is yes. We have very sophisticated tools to simulate on-chip noise components, and you are correct. There are now available on-chip resistors which have sufficiently low noise, switches which have sufficiently low on resistance. It could be done. Yes, it could. I should say this. The reason why some people like digital volume controls, I've done this from the analog point, they're remote controllable. You press a button, the volume goes up and down. You can't beat that unless you put an electric motor on, which I suppose you could, but yeah. Yes, sir?
Repeat the question. I couldn't quite catch.
The gentleman asked if in a chip environment, in a silicon chip environment, could not an analog volume control be made of the required performance? And the answer is, I think, yes, it could. Yep. Yes, sir?
What are the potential sources? I tried to put an analog volume control in the DAC, and it was working.
It was
working.
Yeah. Well,
because it obviously had use no.
Right. Well, it's interesting because, as I mentioned, that graph was from a simulator that we have that simulates analog volume control approaches. And it turns out that simulator is not simple. It turns out that one of the most interesting things is the noise varies depending on the setting of the equivalent potentiometer and peaks mid-potentiometer value, which is a surprise. Right? It doesn't peak at the low signal or the high signal. It peaks in the middle. So you get a very curious graph of signal-to-noise versus volume control setting. But the main, if you say, well, I'm just going to keep reducing the resistance of that potentiometer equivalent because it's often made as a ladder network, I'm just going to keep reducing the equivalent of that till the noise gets low enough, well, then it turns out you're burning a considerable amount of power driving that resistor in order to maintain its low noise. And then it turns out that there's a series resistance equivalently in series with the wiper of the potentiometer that is generating thermal noise into the amplifier that's necessary to drive the line. So that amplifier has to be an ultra-low noise amplifier. The impedance levels at its input need to be certainly sub 1 kilohertz. In fact, I think there's a rule of thumb that in order to beat our Sabre DAC, your total noise equivalent resistance should not exceed about 650 ohms. And that's not trivial to do. Yeah?
I actually built volume control used to interconnect the cable, and I found that there's actually a null in the mid-range of the potentiometer, so I find the lowest noise.
It's in the middle? Oh, that is interesting. Maybe our simulator's not good enough then, because we show that what happens is the source impedance peaks at the point when the wiper is in the resistive middle. Right. And that's what happens. But good comments, and yeah, we currently don't have one. Okay, I have this tendency to talk far too long, and there's a gentleman speaking at 6:15, so I'm going to move on to talking about jitter. And I really think this is the case. Digital audio's weakest link. Everything I said about that hyperstream modulator and measuring the noise is completely irrelevant if you don't first solve the problem of jitter. So I guess I should say that. 2 DACs, the hyperstream DAC and a sigma delta DAC, you will not tell any difference if the clock has got jitter on it. Jitter just kills all the good stuff. Why is that? We're going to visit these topics. What is jitter and why does it degrade the perceived analog quality? What do phase lock loops do? And why does an asynchronous sample rate converter even have any bearing at all on this problem? Digital circuits all have a clock. It's a logic signal at some fixed frequency that instructs the state of the digital machine to move from one sample to the next one. And that clock supposedly occurs very regularly. Here's an example of a 22.68 microsecond clock that's dictating the data flow into a processor of some kind. Jitter is just this. Jitter is the variation of the time interval. And on the left-hand side, we can see it drawn as just the different clock samples and the variation, which, by the way, I made this one have a terrible variation in order to see it clearly. And we engineers tend to always look in this domain. We always tend to look at the statistical distribution of the jitter, meaning almost everybody is coming in at the right value, 22.68. A few guys are very fast, a few guys are very slow. And it's always, well, in a good system, it's a Gaussian distribution. Why does it matter? Well, it's a curious kind of noise. Jitter's an odd thing. It isn't that the DAC has got the wrong value at all. It's that the DAC gives that value at the wrong time. Now, a consequence of that is that when you search for jitter in laboratory instrumentation, what you're looking for is the imperfection, the lack of there being a precise spike in the FFT domain again. And you may be inclined to turn down the signal in search of improving the instrumentation and having a better view of the broadening of the signal. I'm sorry I'm not explaining it in too much detail, but it turns out, I guess I should say this, the error due to jitter decreases with decreasing signal amplitude. So you cannot kind of expose jitter by dropping the signal amplitude. If you drop the signal amplitude, the effect of jitter goes away with it. The DAC has got the right numbers, they're coming up at the wrong time. We want to make the DAC deliver those numbers at precisely the right time. We want a system which exhibits a very sharp characteristic in the distribution of clock times. That one's very bad. There are some slow ones. Sorry, some fast ones, some slow ones. This one's very good. They're all around about the same, and here they are coming in about the same. So clearly then, we'll go out and we'll buy some astonishingly good clocks that are made for the RF industry. You can buy clocks which are sub-picosecond. In fact, some of them are even in the femtoseconds of jitter. And we'll connect that to our audio system. Well, you can't. You can't because that clock must remain in lockstep with the digital data that's being delivered to that audio system, typically from a CD, for instance. So one solution which you might think is obvious, just use a better clock. You can't do it because that better clock has to have the ability to remain locked to what we in ESS call the transport clock, the clock which brings the data, the clock who's giving us the data from a CD or whatever. So what do phase-lock loops do? Well, phase-lock loops solve that problem of remaining in lock. And this is the block diagram of a very typical system. Most systems that we deal with are built in this way here. Namely that the data source, a CD or something, has its own oscillator on board. It's often in a different physical enclosure, and it will send us digital data, and it will send us the clock. And we must build in our DAC, or in our audio-video amplifier, we must build a machine called a phase-locked loop, which is often drawn this way, and the phase-locked loop clocks the DAC, and out comes the audio signal. Problem solved. The phase-locked loop ensures that the local clock to the DAC never loses step with the DAC in the data source, and everything's good, except it's not. Because, once again, it turns out that audiophiles can hear artifacts created by the PLL. And again, to a degree that you would find mind-boggling, to a degree where we used to think that if we had a clock in one of our DVD chips that was at the 1 nanosecond level, that was pretty good. No, it's much less than a nanosecond before the problem of the noise goes away. And it also turns out that the PLL is an astonishingly difficult thing to build in this respect. I don't want to go into too much detail, but very briefly, it's a complicated form of control loop. It's a form of control loop which guarantees that noise gets to the VCO, paradoxically. And it also is very susceptible to extraneous effects. If you try and build a PLL on a chip, it's very, very difficult to prevent that PLL from moving when the digital drivers change, for instance. So it's hard to do. However, that difficulty of doing the PLL has driven many audio engineers to exquisite designs for PLLs. Crystal-based PLLs that have very, very high Q and yet can be pulled to the right frequency. Very high-performance loop filters that achieve lock range and stability even in the presence of noise. Very, very impressive. But what's actually going on is that the manufacturers, the guys you know and love, they're moving to systems now where there isn't a PLL, or there almost isn't a PLL, and I'll show you what I mean. They're moving to systems like this, where they say the DAC is the guy who is sensitive to the jitter. So I'm going to give him the best fixed frequency clock I can. There he is, straight into the DAC, nothing in between. And rather than ask the DAC to synchronize to a data source, I'm going to ask the data source to synchronize to a DAC. So I'm going to send a reference signal to the data source, and he is going to have the problem of the PLL, and he is going to make his source line up with my oscillator. Now, there are many different buzzwords for that technique used by the different manufacturers. They work very well, except that you have to go out and buy their CD player, their Blu-ray player, their whatever, because it has to accept. That I set my phone to remind me what time it was. That's not a call coming through. That's just to remind me to stop talking and get on with it. Pardon me. Right, so that's a good solution. Nothing wrong with that, except that you need to go buy new equipment. But it's a good way to do it. And as I mentioned there. But let's go back to first principles again. Remember what the problem was, that I know I can make a very, very good clock to my DAC, but I can't just do that if I cannot maintain synchronicity with the data source. So that's actually the problem. It's that an ultra-low noise DAC clock will eventually, because this is how things work, it will eventually drift out of lock with the data source. So what is an asynchronous sample rate converter? And however does it help? I told my wife she'd be starting in this presentation. That really is my wife. That really is my chicken there. The problem is analogous to this one. Each day, my wife goes out to collect eggs from our chickens, and the chickens are irregular. They don't actually lay an egg every day, as some people think. The chickens' egg laying and the days do not remain locked. They become asynchronous one to the other. so that if you make a table of the eggs that you collect, it looks something like this. From the few chickens that we have, a few eggs, but one given chicken, yes, it'll give us an egg, yes, no egg today, yes, no egg today, like so on. Now, that is about what goes wrong with the perfect clock to the DAC and the data source. The data isn't always there. Sometimes when you want an egg, it's not there. Sometimes when you need the new sample, it's not there. But, surprisingly perhaps, there is an algorithm that, given the egg schedule, and that's the egg schedule from a chicken on the last page, collected at 8 a.m. every morning, there is an algorithm that can calculate when the egg is halfway out of the chicken. Right? So you can actually do that. So, I could tell the wife to go out with the camera at 2:15, the chicken's about to lay an egg. But I'm making light of it to make it easy to understand, but it's true. There is an algorithm that does that. Now, because that algorithm exists, that must mean that, in principle, we should not need a phase-locked loop, even though the systems are asynchronous, because there's a way the digital circuit, with its own clock, corresponding to my wife going out at 8 a.m. every day, despite not having anything happening other than at 8 a.m. every day, it can accumulate knowledge of, a system representative of, when the exact egg comes out, when the exact sample arrives. And in fact, that's what the ESS Asynchronous Sample Rate Converter does. It's not the same as the analog device's Asynchronous Sample Rate Converter. What that does is you give it two sample rates and it changes one sample rate to another. This guy not only changes the sample rate, it knows where it does. How can I explain this? You just give it the data in the other domain, and it figures out how to correct the error in the. I'll show you. This is the drawing here. See, you can connect the world's best oscillator you can buy to your DAC, and you can buy some very, very good oscillators from the RF guys. They are very, very low noise oscillators. You can connect it to your DAC, and you don't need to send that signal to the data source. The data source just does whatever it did before. This little box here runs the when did the egg appear algorithm, and it gives a signal to the asynchronous sample rate converter, telling it when the actual data mathematically was. You got it at the wrong time. I'm sorry, you've got the wrong clock. It's not phase locked to this guy. You got some data and it's garbage. But in fact, that data should have been exactly here. And this guy knows where the data should have been. That digitally recovered transport clock is not a clock. That is not a clock to this guy. That is a digital data bus which is encoding where the mathematically correct place was that the data you got in error should have been. Now, when you do all that, it means that this system has extremely low jitter at the DAC and doesn't care what the data rate is coming from a source. So you can hook it up to any of your existing data sources. Okay. Now, you're going to ask me, you're going to say, well, therefore, Martin, what you've just done is you've just hidden all the cleverness in whatever that asynchronous sample rate converter does. And to some degree I have, and I pondered this question until approximately 11 a.m. this morning. I thought, I have got to show how this asynchronous sample rate converter works, but it beats me. It's so complicated to describe to you how this A to D converter works. I can only do it in the not A to D converter, asynchronous sample rate converter works. I can only do it in the very broadest outline. But the good news is, if you're interested to know in detail how this works, just go read these patents. There are 3 patents that go into fabulous detail of how it works. But in hand-waving terms, prior attempts to do this have always necessitated the creation or destruction of samples in the data stream. This asynchronous sample rate converter does not do that. In fact, it turns out mathematically it only has to make a slight modification to approximately 1 in every 600 of the samples that it gets, and that modification to 1 in every 600th can be made to remove all the artifacts due to the asynchronous nature of the clock. Okay. So that's in the Sabre DAC chip as well. So you can put in any clock you like. It doesn't have to be a multiple of the audio signal from 20 megs to 100 megs. Any clock you like. The audio will not suffer degradation to PLL. There is no PLL. It's entirely a digital system. It's entirely a high-quality clock. And again, I know this is to some degree a tease because you want more details. Email this lady again, mention the Rocky Mountain Audio Fest, and Wendy will send you more documentation on how this works. This is the last slide, and I'm sorry I'm running late. We're getting quite an audience behind us. We try to make the best DACs and ADCs we can for you guys, for the guys who appreciate digital music at the best it can possibly be. And I won't go through them again. I've spoken about some of them. There are a bunch more. Talk to us, contact ESS if you're interested to use our chips inside your products. Do go and listen to products which contain the Sabre DAC. There's a few of them here at the show, and the ones that don't. And I do believe you will see the difference. Thank you very much.